What you just saw is the only protection of this power plant against water hammer effect in case of any emergency. This pressure releasing valve opens only 20% during the startup sequence for just a few seconds, and if this valve does not open during the startup sequence, the unit startup does not proceed further. And before you guys ask me in the comment section why only 20%, this opening is only to confirm that pressure relief valve is working normally, and in case of an emergency this valve opens fully to release the high pressure. So every hydropower plant follows its own startup philosophy. Every machine has its own protection, interlocks and operating procedure. But today we are going inside the complete startup sequence of this 470 megawatt hydroelectric unit from total standstill all the way to synchronization with the grid. So this startup consists of 10 major steps before a single megawatt reaches the transmission system. The startup begins from ST condition, which is known as standstill condition. At this moment, the turbine runner, generator, rotor, and main shaft are completely stationary. And interestingly, the first priority is not generating electricity; it's protecting the machine. And before this joint can even move, the automation system starts a long checklist of auxiliary systems. For example, lubricating oil pumps, cooling water circuit, shaft seal water system, moisture removal system, and bearing cooling arrangement, carbon dust extraction system, and high pressure oil lifting pumps. Watch the screen carefully as every system starts one by one. And before rotation begins, the high pressure oil lifting system injects oil beneath the rotor to create a microscopic oil film that slightly lifts the 100-ton shaft off the thrust bearing pads. This prevents metal-to-metal contact and protects the bearing from severe startup damage. Only after every auxiliary parameters become healthy does the control logic allow the sequence to continue. As you can see on the screen, systems now enters into the step 2, which is opening of bypass valves. This valve opening is very important for equal pressure. You can see full details about this bypass valve here. I have highlighted the motorized valve of bypass pipe here. Keep an eye on this motorized valve as they begin opening, and listen carefully to the sound of filling water. Pressure of head external is 10 bar, as the available water head here is approximately 110 meters. That's considered relatively low head for hydropower. So to achieve this massive 470 megawatt output, the plant relies on extremely high discharge flow, roughly around 1,15,000 gallons of water every second. Now that pressure is balanced on both sides, the main inlet valve or MIV can safely begin its opening. And yes, many of you asked about the size of this penstock in the previous video. The diameter of this penstock is about 10 meters. I will speed up this section up a little so that you can see the important movement. Watch carefully. The MIV gradually moves towards a fully open position, and notice something interesting. As soon as the main inlet valve fully open, the bypass valves close again automatically because their job is finished. At this point, water is now available inside the turbine spiral casing, but the turbine still isn't rotating because the wicket gate remains nearly closed. So hydraulically the unit is prepared, but mechanically it is still restrained. Then comes the step number 4 and 5, pressure relief and safety verification. In the start of the video, I've told about pressure relief valves. Now this is the most critical part of the entire startup, pressure relief verification. Systems such as the upper pressure relief valve and pilot pressure relief valves are tested to ensure that they can react instantly during emergency condition. And remember that PRV we talked about earlier, right now it is the most important component in the powerhouse, because if a sudden load rejection occurs later during the operation, these valves must open immediately to release dangerous pressure surges before they become destructive. This powerhouse has no surge shaft, which means these PRV systems are the primary defense against hydraulic transients and water hammer effects. If the valve fail this test even once, the startup sequence stops instantly. The unit goes nowhere, no exception. With the safety valves verified, the machine is now officially authorized to move. But before water can strike the runner blade, the physical locking system must be removed. After this, then comes the step number 6. Remove turbine auto lock. During the shutdown, mechanical locking pins, hydraulic brakes, and parking device keeps the turbine shaft secured against unintended movement. Now these protections are removed. This is the moment the turbine generator transforms from a static mechanical structure into an active rotating machine. And hence this lock disengaged, the next step become impossible to ignore. Okay, step number 7 and step number 8 is governor activation and turbine acceleration. The hydraulic governor provides the physical force needed to move the wicket gate. Meanwhile, the digital turbine governor or DTG acts as the brain of the entire speed control system. Together, they constantly regulate turbine speed. In simple terms, if electric load changes, the turbine speed tries to change with it. The governor detects that instantly and adjusts the wicket gate opening to stabilize rotational speed. Now, the startup enters its most dramatic phase, turbine acceleration. The digital turbine governor carefully commands the hydraulic servo motor connected to the wicket gate. Very slowly, the wicket gate begins opening. Controlled water flow enters into the runner, and for the first time during startup, the turbine shaft begins to rotate. As the rotor accelerates towards the rated speed, the entire powerhouse starts changing character. You begin hearing deeper mechanical resonance, vibration increases. Massive rotation components comes alive. The machine transitions from silence into controlled power, and remember the PRV system is still standing by. Because if anything trips during acceleration, it immediately becomes the most important protection systems in the plant. Step 9. Initially, the thrust bearing still depends on high pressure oil lifting system, but as rotation speed increases, something important began happening naturally. Hydrodynamic lubrication develops. Think of this as the moment the machine stops walking and starts surfing on a wave of oil. The rotating shaft drags oils into the wedge-shaped film beneath the bearing surface. That oil film becomes strong enough for the rotor to effectively float without direct metal contact. Once this stable oil layer forms, the control system automatically shuts down the high pressure lifting pump because they are no longer needed. And this is the major milestone during startup. It confirms the machine has reached stable rotational behavior. Then step number 10 is the excitation and no load operation. Okay, now the turbine is near rated speed, but the generator still cannot produce electricity because rotation alone is not enough, and the generator now needs excitation. So the excitation system supplies direct current into the rotor winding, creating a powerful rotating magnetic field, and this is where the invisible physics finally become electrical power. As the magnetic field rotates inside the rotor, electromagnetic induction begins generating voltage at the generator terminals. The voltage gradually rises towards rated value, and this is the moment where a simple spinning machine transforms into an energized generator. And at this stage, the unit reaches SNL condition, which is called as speed no load. The machine is now spinning at full operation speed and producing full voltage, but it is still disconnected from the electrical grid. So even though the generator is energized, it is not yet delivering real power. And then the final step is synchronization and generation. Now comes the final command. Operator gives the final command of synchronization. The governor stabilizes turbine speed. The excitation system stabilizes voltage. Meanwhile, protection system continuously monitor vibration, bearing, temperature, oil pressure, cooling water, shaft condition, and electrical parameters in real time. So everything must match perfectly: frequency, voltage, phase angle, and grid connection. So here on the screen you can see the frequency, voltage, and phase angles are being aligned, and then when these parameters are aligned, the generator breaker or GCB closes at the exact instant. This machine stops being only a rotating mechanical system and becomes a 470 megawatt power producer connected directly to the electrical grid. All of this happens through heavily automated SCADA controlled logic. Because even a single startup mistake can result in overspeed, destructive vibration, bearing failure, electrical faults, water hammer, or catastrophic penstock damage. That is why every interlock, every valve, every protection system, and every operating condition is verified step by step before the machine is allowed to move forward. Because inside a hydropower plant, safety is not just part of the startup sequence, safety is the startup sequence.